Hello everybody, my name is NGUYEN from National Institute of Advanced Industrial Science and Technology, Japan. Today, I would like to introduce our recent research topic with the title, An On-Reduce Algorithm and Network Co-Design for Large-Scale Training of Distributed Deep Learning. First of all, I want to emphasize that our target in this work is to speed up the process of training deep learning by reducing the communication time. For training deep learning in parallel, commonly people use the data parallelism approach, which requires a collective communication between computing nodes at each iteration to transfer the weight of the learning model. Typically, deep learning models are very long in size, so that the communication becomes bottleneck. To deal with this problem, there are several approaches along the training stack. For example, optimizing the communication algorithm, data compression, or overlapping the communication and computation. In this work, we are speeding up from the network architecture point of view. Specifically, it's important to note that the diversity in link bandwidth in the hierarchy of interconnection network leads to a reduction in communication throughput, one of the most important factors when communicating long messages. We address the issue by proposing a novel co-design of on-video algorithm and network architecture. Note that both data compression and overlapping could be used on top of the solution proposed in this work and do not conflict with our solution. Now, let's move to the detail of my talk. First is the motivation. Nowadays, we have already seen that deep learning has been applied in more and more real-life applications, such as healthcare, robotics, or science simulation. However, because the training phase needs to process a huge computation so that it takes time and limits the development of new deep learning applications in new domains. For example, GPT-3, a natural language processing model, is estimated to train in 355 years on a single GPU and costs about $4.6 million. So that training a deep learning model in parallel on supercomputer or high-performance computing system become common. Typically, we use data parallelism, which applicates the deep learning model in each processing element, such as CPU, and splits the data by the number of samples. Data is processed in batch iteratively. After each iteration, processing elements have to share their local information to update the weight that performs the on-reduce collective communication. Parallel training in multiple GPU have to cut down the training time, but the scaling is not perfect, and the communication between the CPU will add an extra overhead. So in practice, it will take more than $4.6 million to finish training one epoch of GPT-3. Moreover, when the deep learning model becomes deeper and bigger, such as from 10 million of parameters or billion of parameters, and when increasing the training scale, such as from 10 GPU to 1,000 of GPU, communication becomes main bottleneck. To deal with this problem, there are several directions. First is to optimize the communication algorithm by using ring-based algorithm, which cause latency factor and bandwidth factor, and as you see in this slide, and in it, P is the number of CPU or processing element. Alpha is the time for sending the message from source to destination, and also known as startup time. And beta is the time to inject the 1 byte of data into the network. Typically, it's the inverse of link bandwidth. Ring-based algorithm is well known and is bandwidth optimal, but it leads to a linear increase in the latency factor. Other approach is data compression or communication and computation overlapping. However, when scaling out, the interconnection hierarchy of modern HPC systems leads to a gap in latency and bandwidth factor, alpha and beta, and a different interconnection network. Network relatively have a higher network latency and lower network bandwidth in the comparison with the intra-node network architecture. Especially when training in longer scale, for example, thousands of workers, the routing path length increase with the number of involved processing elements on CPU. For example, from 4 hops as in the 2-level factory to 6 hops as in 3-level factory. It's reduced the performance benefit of ring-based algorithm in long scale. Since the linear number of steps p minus 1 cannot be ignored because it becomes thousands of steps, and each step incurred an additional delay to performance switching at the high predict level 3 switch. For example, 40 nanoseconds per switch at in a 3-level factory. In this case, an alternative way is to use algorithm which requires only logarithm of p step. And in this slide, I want to quickly summarize the algorithm named the vector halving and distance doubling Allreduce algorithm, which have logarithm p of step. So as for short, I will call this SD algorithm. The SD algorithm is also a combination of reduced scatter implemented with the recursive data halving and rank distance doubling, followed by an on-gather with recursive data doubling and rank distance halving. At each step, this processing element E is paired with the processing element E plus 2 power of Z to send and receive different segments of data with the size n divided by 2 power of Z. For example, at rank, this is we have at rank here, and each rank keep one different type of data. The number 1 here is the rank. The number 1 to 8 is the value of the data inside the rank bunch. At the first step, the first rank will send the in pair with the second rank, and the first rank will send the segment data from 5 to 8 to the second rank, and the second rank or second processing element will send the segment data from 1 to 4 to the first processing element. And after the first step, the processing element wants to keep the reduced value of data segment from 1 to 4 of both 1 and 2, and the processing element 2 keeps the reduced value of data segment from 8 to 5. And similarly, after 3 steps, each processing element keep 1/8 of reduced value of on the rank. In overall, this type of algorithm can reach the lower bound of the bandwidth factor. It's also the bandwidth mean bandwidth optimal, but it's only required 2 multiple logarithm p of step for latency factor. So it sounds good when compared with the ring-based algorithm. However, in practice, the cost of this algorithm increases significantly if the number of computing nodes is not the power of 2, or when the length of communication path is occurred p by 2 or more flow at the same time, or the network condensation happen. This figure shows the 2 cases that network condensation may happen in the current SPC system for training using the ring-based algorithm, using the SD algorithm. The first case is the condensation at the NIC, network interface controller at level and switch, when 2 processing elements share the same link of interconnection, inter-node communication. The second case is in a condensation in the link between level 1 and level 2 switch, when all the processing element of the first level 1 switch has pair with all the processing element of another level 1 switch. Since the HD algorithm use the same rank distance for all the P processing element at one step. Even with the non-blocking factory network topology commonly used in modern SPC system, the second condensation case still sometimes exists because the routing is not perfect balance in practice. The figure in the left side shows the communication time versus the number of flows that share the same routing path at the same time. Communication using the proposed SD algorithm may be increased up to 2 times by condensation occurred, while the communication time of ring-based algorithm nearly do not change because there's no condensation in ring-based algorithm. So the question here is how to apply the SD algorithm effectively is important. So in this context, we propose to use the family of network topology that is exploiting the small one network model. And we start from the small one network model such as Boloas and TRUONG model and names distributed loop network. in which N node are placed in a ring, and each node E has log N shortcut link that connect to the node E plus 2 power of k, where k is from 0 to log N. And we apply such kind of network topology to the network of switch in our architecture. Apply into switch network topology, we arrange P power of 2 switch in DLL, where each switch has wide downlink and each shortcut link have be arranged to multiple physical link or cable. Such network has logarithmic degree and have direct link between any pair of switches in the communication part of ring-based and HD's algorithm. Study in our proposed topology has which is somewhat comparable to factory network topology in terms of scalability that has a clear advantages in reducing the communication latency. To mitigate the network contention for HD algorithm, we propose a topology-aware algorithm we name shifted halving doubling or SSD to fully utilize all the inter-switch link. Our aim here is to utilize the shortcut link effectively by allowing processing element in a switch to use shortcut one shortcut at each step. Assume that we have two Q power 2 switch and involved in training. The SSD algorithm including intra-switch communication that's similar to SD algorithm and inter-switch communication. In the second phase, inter-switch communication, at each step G, a processing element E of switch Q is paired with the processing element E in switch Q plus 2 power of I plus Z mod Q. This, in the ideal case, the X shortcut is used by only one processing element a step, and there's no contention. For example, in this example, you see that for the inter-node communication from step 2 to step 3, each node here, each rank here, you want different shortcut, so it can do not raise any network contention. And this is an equation, so the code of SSD algorithm in which alpha I, alpha O, beta I, and beta O is the latency and bandwidth factor for intra and inter-switch communication respectively. And we also have some case that we can, it's not idle. For example, in the case of Q more than 2 power of P, so we divide the network into two different groups. Then we perform the SSD inside each group like this. And after we finish SSD inside each group, we will use SD algorithm to SD algorithm for communicating between groups. The network contention will happen when we do communication between groups, because we have 2 power of P flow use the same inter-switch link at the same time. So we have the contention penalty or cost for contention is something like this. Another case is the case where Q less than 2 power of P, and so we also divide network into 2 power of K above to a group. Like you see here in this figure is the group with the white color and group with the red color. So we also perform the SSD algorithm inside each group and communication between group after the SSD. And we also meet the network contention when virtual groups use the link for inter-switch communication at the same time. And so this is a contention penalty and cost for this. In general, the contention penalty is sum of those two values, and we show that it's always smaller than the contention caused by SD algorithm on the DLL distributed loop network architecture. And you can find the detail of our improvement in our paper. I will keep this in this talk due to the time limitation. Now let's move to the evaluation. In this section, we use a SCIM-grid simulator to evaluate the performance of Allreduce microband match. And we use factory plus ring-based algorithm is the baseline and compare the communication time of Allreduce microband match as well as the training time of real workload on the baseline with our proposal. We use those parameters for configure the network, and more you can find out the more detail in the paper. First of all, we have the micro benchmark result. In overall, you can see that the ring-based algorithm for our DLN network is slightly better than that on the factory network, but it's very small, about 2 to 5%. It's because of the reduction of latency factor when changed from multiple level factory, for example, for 6 hop to 3 hop, where we have the direct connect between the node. Secondly, we see that the DLL with the SSD algorithm is significantly better than factory ring algorithm, the baseline. For example, in the case of 256 CPU, we can reduce the time about 31%, and in 1K CPU, we reduce the time 90%. First one is when we compare our algorithm proposal with the factory and SD algorithm, it's still better about 50%. And when we compare our proposal with the DLL SD, the new network architecture distributed leaf network, but use the own algorithm, our proposal is still better about 25%. Although, in addition, although both family of own algorithm are bandwidth optimal in theory, the halving doubling algorithm family is more sensitive to the change in the message size. It implies that the exiting of network contention in this case. Moreover, there's a crossing point when SD family algorithm become worse in competition with the factory ring algorithm. For example, this point or this point. And in this case, it may be here or here somewhere like this. When the number of GPU increase, the point also increase, for example. And it implies that our proposal can work well with the large scale or in the case of small message size. For the real one workload results, we try to simulate the workload of training RedNet 50 and VGG. We have message size of about 82 megabytes or more than 550 megabytes. We use the data set is EmmitNet, about 1.8 million of emit, and you batch size of 32 samples per GPU. It means that for the case of 256 GPU, we have 157 iterations per epoch. And this figure shows the execution time to training one epoch. And we break down the time into the computation and communication. And you can see that our proposal can help to improve the training time about 50% compared to the baseline in most of the case. Or some cases only 30% or 40%. But when you increase the number of GPU, so our proposal can have gain more performance. Yeah. In overall, in summary, I want to emphasize that our target is to try to speed up the process of large-scale training deep learning by reducing the communication time. We do this by proposing the distributed loop network topology plus the shift halving doubling algorithm optimized for that kind of network. We can help to reduce significantly the communication time when scale up. For example, we can reduce up to 90% of our communication time. And we apply, and note that our proposal not only apply for Allreduce algorithm, we can apply for different type of connected algorithm like on-gather and reduce scatter. See, the discussed and Allreduce halving doubling algorithm as a combination of those connective operation. That's all. Thank you.